All right, party people. Now, the last, I am almost the last part. I need to teach you some calculation as well. But now we know how to, we know what area we need to find, right? We know the notation. But now we need to learn to convert that into values. When we say phi of A, how do we convert that into, how do we read that area essentially from the Z table? So this is your introduction to the Z table. This is your Z table. Now this region here is your Z values. I'll teach you what these represent, This is your normal distribution curve. As you can see, the formula of negative phi I taught you before. This is your normal. It signifies that all these values will be of less than. They'll give you the area of less than, right? Anyways, and by the way, in normal distribution, less than, equal to are the same thing, and greater than equal to are the same thing. So it doesn't matter. The inequality does not matter. All that matters is which side it is facing, greater or lesser, right? So do not worry about that in any way. Okay, so now let's look at a question. For example, it says ages have been normally distributed. Actually, X has been normally distributed with the mean 40 and the variance 20.8. ठीक है? So this is the mean represented by mu, and this is the variance represented by lowercase sigma squared. ठीक है? This is the variance, this is the mean. So the question says state the probability that X is the ages are less than 50, 50 years. ठीक है? So, okay, you're like, okay, since the mean is not zero and the variance and standard deviation are not one. By the way, all your questions are going to be non-ideal, so do not worry about that. You're going to always use the standardization formula first. How do we do that? We simply do this. 50 is your value, which you need to make it ideal. This is a non-ideal value. You need to convert it into ideal. So minus the mean, which is 40, divided by the standard deviation, not the variance. So how do we do that? Standard deviation is under root the variance, right? So that's going to just cancel out. So under root the variance is 20.8, and this value is going to now turn into ideal. And when it becomes ideal, I taught you, X turns into Z. Now you will get a Z value, which you will read from here. This is your Z values, all the Z values, right? So this X turned into Z, and because X was non-ideal, Z represents all the ideal values. That's the way to do it. Okay, so you make the brackets, you say probability. It's the same thing, right? So let's get you the value. Z is less than, let me get you the answer. Wait. Okay, so the value I'm getting is 2.1926. Now keep in mind, from the Z table, you can only read to 3 decimal places. How far can we read? Till 3 decimal places. And that is the rounding off you're going to do. What are you going to do? You're going to round off whatever your value you're getting, no matter how big or how small, you round it off to 3 decimal places. So 2.1926 is going to turn into 2.193. 26 right? 26. So I'm going to write 3. 3. There we go. That's 3 decimal places. Good enough. Now we read it from the Z table. So hear me out. This is your, these are the first two. This is your main value, your ones, and this is your first decimal place. You read these two from this region. This is where you read the first decimal place from. This is called the first decimal place region. Okay, you read the first decimal place from this whole region. So, and by the way, take care of your one's value as well, right? One's value has to what fit as well. So you cannot just go for 0.1, right? You need to the first decimal place is read from this column. So 2.1 is our first decimal place. So 2.1 is right over here. Okay, now you located that. The second decimal place is read from this big old region. So you're gonna read the second decimal place from this region. Okay, so that is 9. So we have 9 right here. Now see where these two values collide. 2 point would be somewhere right here. As you come down from here, this is the value. So this is the value you're getting. Now we've read it till here. 2.19 has been read. 3, the last and third decimal place is read from the last column, which is the add column. Now keep in mind, these add, the name mentions it, right? You're gonna add it to the main value you have found from the first and second decimal readings. From the first and second decimal readings, what did we get? we got this. We got 0.9857. 0.9857. Okay? But the last decimal place represents an add value. Now, what is an add value? Value is simple. It is to be added. It is an add value. Huh? It's supposed to be added, but it is supposed to be added very specifically. How? Let me tell you. These values are already in the powers of, for example, it's 3, right? So 3 is right here. And if we collide it, by the way, make sure it is in the same row, right? So in the same row, the add value is 2 point, okay, 1. So we had 1. 1 needs to be added. But 1 is not just added in the whole decimal, 0.9857 plus 1. No. This 1 value is already in decimals. In what decimals? In your standard form, we write it as 1 into 10 ki power minus 4. So the add values are already in 10 ki power minus 4, right? So whatever value, 30, if you read 35, you're going to go 35 into 10 ki power minus 4. You read 19, you're going to go for 19 into 10 ki power minus 4. And this whole thing is going to be added to the value that you found using the first two decimal places and your ones value, of course. So now add this up, what do you get? You get 0.9858, and that, my friends, is your answer. Area equals to probability. By the way, the notation would have been phi of 2.193, and then you would have read it first decimal place read from this column, z column, that gives you 2.1 here. The second decimal place read from this big column, you match the values where they both coincide, you got this reading 0.9857. Then the last decimal place is an add value. Add value is read from the add column. Now you see where they coincide with the 2.1 row, and they coincide at 1. Now keep in mind, add values are already in the powers of 10 ki power 10 to the power minus 4. So we are going to add it to the main value which we found from the first two decimal places, and add 1 into 10 ki power minus 4 to it, and then you get your final answer. Another way to add it would have been something like this, but I'm not going to show you that actually. This is way more authentic and way better for you. So now let's do one on your own, please. Probability x is less. Actually, now I'm gonna make it difficult. X is greater than 55. You already know the mean. The mean is 40, and the standard deviation is under root 20.8. Okay, so raise me, please. Probability. I'm gonna standardize it, right? So now x becomes z, because now we're talking about the standard normal curve, right? Our data was distributed normally, but it was not standard. The standard normal curve has constant probabilities because every kind of data was making the same shape of the bell curve. So we said, okay, if this data takes this area, it has this probability. This area, it has this probability, and all types of data taking that shape can be represented through that probability. We made our lives easier, basically. So how do we do that? So z is greater than 55. Subtract the mean, divide by standard deviation, that is 20.8. We do that, then you get the answer. Okay, so the value you're getting is z is greater than 3.289. There you go, round it off. Okay, now there's a very specific, you already know by the way, which area am I finding? Draw the normal distribution curve, make the 0. 3.289 would be somewhere around here, right? And people, and then you need to find what, this area, greater area. So I can subtract 1 from the total area minus all the area that is less than 3.289, and I'm going to get the greater area, right? So 1 minus 5 of 3.289. That's not a problem, but this is a very specific problem. See, what is my first decimal place? 3.2, including the ones. 3.2. Okay, sir, you said read it from the Z column 3.2. Oh, wait, what, sir? So what is happening? It ends at 2.9. What is this scenario? You said that the deviations are infinite and all these values should be included in the Z table. Why aren't they included? Well, my friends, there is a very specific phenomena occurring. I did this on purpose, by the way, so you know. Knowledge, see, knowledge is way more important than just doing your maths P52 paper, right? So take this knowledge. See, what the mathematicians observed is that the deviations, yes, they are infinite, theoretically, but mathematically, most of the data is already covered when we go 3 standard deviations to the right from your mean and 3 standard deviations to the left from the mean, the deviations are always covered in that region. 99, not the 100% of the data. Approximation. Maths is always about approximation on higher levels, right? So, by the way, these are very authentic and close approximations by merely a few decimal places, right? So, 99.7 something percentage on average of the data is already covered when we move 3 standard deviation to the right and 3 standard deviation to the left from any mean. And that could of course be different regions of the your infinite sort of curve, but most of the data always fit into 3 standard deviations to the right, 3 standard deviations to the left. And what is your standard deviation? 1. In an ideal case it is 1. So 3 times, so 3 to the left and 3 to the right. Most of the data that was normally distributed was always covered in that region, 3 to the right and 3 to the left. So we said, okay, 99% of the data is being covered. We do not need to waste our times. We're going to fit all that data into that region. So if you read that and that, you can read the key to understand this. These are multiple normally distributed data, like this one, with the mean and standard deviations of non-ideal data can be standardized into z-scores on the x-axis that are actually values. Only the context will change, but the data and probabilities, the curve will remain the same. So why did I get this value? Because my friend, I just took a random 55. This is not normally distributed data, right? This was just a random 55, random mean and random standard deviation I just picked out of somewhere, right? Anyway, so let's just do one final question. Probability x is less than, actually let's do x is greater than, why not? X is greater than 40. Let's do that. Okay, no. 40 would just become 0 or something, right? Actually, we can do 0. Let's do this. So if I standardize this, this will become 40 minus 40 divided by standard deviation, which is 20.8. This gives you probability z is greater than 0. 0.0. By the way, these are real numbers. Now, another thing I'm going to tell you is normal distributions is basically always going to be your the study of continuous data. Continuous data is always in real form, as in decimals. So make sure you're using decimals. Even though this is going to give you 0, you're going to write 0.0. Okay? So how do we read it from the z table? Very simple, people. You simply go for okay 0.0. So that would mean probability. Oh, by the way, first correct the. Let's make an equation. So I'm finding all the area that is greater than 0. That would mean here's my curve, here's this, here's the 0, all the area that is greater, so that's on the right, all this region. In this specific case, it starts from the center and moves to the greater part. So if it starts from the center and moves to the greater, both sides are just 50%, right? That's 0.5 in probability. So it doesn't matter. I do not need to subtract by 1, or I do not need to judge it. I can simply say it's 0.5. And if we read this from the z table, 0.0, that's it. So 0.0 is 0.0, and they do give you a 0, right? Because see, there are no where did we go? There it is. There are no further values, so you can just agree with it that it is at 0, 0.00, because what I can write 5.00 and the value does not change, the meaning does not change, right? It's still 5, but making it readable for the normal distribution for the z table, I'm going to use that. So 0.00, because since there are no more decimal places, I'm going to use 0 value, and this is equal to 0.5. So that is one way to do it. Now this was just some fun cases to help you understand how this works. Now let's get into some more of the calculation of how differently you're going to tackle this. Now we know how to read the z table. Simple as is, first decimal place and the ones value will be read from the z column. The second decimal place is read from the second large 0 to 9 column, as in this whole big column. And the last decimal place, which is the third decimal place, is read from the add column, and the add column has values already exponential to 10 to the power minus 4. So whatever you read, you add 10 to the power minus 4 to it, and then that whole chunk will be added to the main value, which you read from the first two decimal places, as we learned over here. Simple, right? So we're going to do more examples and then we're going to do some question types on how different cases will be judged. All right, so let's just do one more question for safe measure. So we have complete command over what we're doing. Okay, so we need to find the probability of a non-ideal variable x, which is less than 45 and greater than 37. Okay, so first idealize it. We know that the mean was 40 and the variance is 20.8. Okay, so 37. How to standardize it? How to idealize it? Minus the mean divided by the standard deviation. That's 20.8. Now, as it is being idealized, it is no longer x, it is now z, right? Because now we're talking about the standard normal curve. 45 minus the mean divided by standard deviation, same thing over and over again. Now both of these turn into z is less than blah blah blah. Okay, so let me get you answers. 37 minus 40 divided by under root 20.8, and we have minus, so round off to 3 SF, so negative 0.657, sorry, 658 actually. It's double seven, so I'm gonna round it off to 8. Anyways, and for the other part we have 45 minus 40 divided by under root 20.8. Now I'm getting 1.096. Okay, so these are two z values. We call these critical values as well, because that is a terminology the examiner uses. So I'm going to use it too. Anyways, so what do we need? Now let's imagine what area, what probability do we need to find? Probability of whatever z is, it should be less than 1.096 and greater than negative 0.658. So which area do we need? Let's imagine it. So I need this. Here is the center, 0. And now 1.096 will be somewhere around here, 1.096. So make a boundary there. Negative 0.658 is going to be somewhere around here. Make a boundary there, 0.658. There we go. By the way, this is not the best, imagination, but it works. Okay, so and if you color that up, this is the area you will need that will equal to your probability to answer your question. So how does that work? Okay, so if I find all the area that is less than 1.096 and subtract from that all the area that is smaller than negative 0.658, so will I get this region in between? I will, right? So I'm going to do that. So how do we find area that is less than 1.096? We say phi of 1.096. Right? Subtract from that all the area that is before negative 0.658. So phi of negative 0.6. Now we know due to symmetry, this value cannot be first. Firstly, we know this value I cannot find. I do not know how to find, right? But I know that due to symmetry, this value will be equal to 1 minus phi of the positive value of the same thing. So 0.658. And subtract it there, the bracket is going to remain, and phi of 1.096. There we go. If we open the brackets, this is our final equation is going to be 1.096 minus minus plus. So there you go, phi of 0.658 and then minus 1. Now let's learn to read this from the z table. Read this value first, phi of 1.096. So first decimal place is read by the z value, is the z column. So 1.0. Let's find that first. 1.0 is right here. 1.0 is found. The next is 9. So 9 is the second decimal place that is read from this big column. So 1.0 and 9 is all the way at the end on this value. So this is our main value. The last decimal place, the third decimal place is read from the last column, the add column. So first let's just note this down, 0.8621. So I'm getting, here we go, 0.8621 plus, now these values have been read. The last decimal place is the add value. So look at the add value, it's 6 and it should coincide with this column. So 6 right here. It coincides. Yep. So 14. 14 is the add value, and I've told you add value by the name you already know. Add value is added to your main value, and it is already in standard form, which is 14 to the 14 into 10 to the power minus 4. So please do not forget this exponential here. If you do that, then well, you're screwed because you will lose marks. See, it is already add values are already in this notation. They're just values written there, but it is called for that they need to be multiplied by 10 to the power minus 4. Okay, so moving on. Do the same for this one. So zero point 0.6 is our first decimal place. That is right here. Zero point 0.6. Next we have is 5. So 5 is 1, 2, 3, 4, 5. Right here. So our main value is 0.7422. Okay, so let's draw a bracket 0.7422. Now let's find the add value, which is 8.7422, and now 8 is right there. What does coincide with this? 26 coincides, so I can simply do that. 26, but it is already in a specific form, which is into 10 to the power minus 4. So we have that, and then from when we find both these, add them together and subtract it from 1, and then you get your final answer, which will be, let me get you that. Okay, so our final probability is 0.6083, and that is our final answer. So all of this working, I mean, like kitni hi working thi, such small working, precise, conceptual, all this is like 5 marks in your exam, right? 5 to 6 marks. So easy marks, do not lose these, man. Definitely getting in them. Now we know how to read the Z table. There is another part. Moving on to that.